Hi, this is Physics 503, Nuclear Physics, and in this lesson we're going to discuss about the atomic nucleus. So before we proceed to our actual lesson on the atomic nucleus, let's have first some review of some basics in the atomic scale. So we have first your Bohr's atomic model. I think your Bohr's atomic model is the most widely known model of your structure of your atom. This is similar to the miniature solar system where your electrons orbit around a central nucleus. It's so common that you can actually see Bohr's atomic model in many logos of various physics organizations. But as we know, your Bohr's atomic model actually do not actually describe the real picture of your atomic structure. But this can serve as a simplified model of the quantum model. Well, you know that the actual structure of your atom is not like this one where you have your electrons orbiting around your nucleus, but instead you have your electron clouds. Okay, what we have is a probabilistic distribution of your electrons, not something like this one where you know exactly where your electrons are. So this is, however, can serve as a simplified quantum model where the electrons are described by 4 quantum numbers. And you have here in your Bohr's atomic model quantum levels or shells for your energies. In your Bohr's atomic model, electrons occupy certain orbits that are stable and are called stationary orbits. So you have here, this blue one is your positively charged nucleus. And then you have orbit 1, 2, 3, 4, which represents your K shell, your L shell, your M shell, and your N shell respectively. These are stationary orbits, and your electrons occupy certain orbits here that are where they are stable. Each orbit has an energy associated with it. And the farther the orbit from the nucleus is, the higher is the energy. Electrons fill this orbit in such a way that you have your 2n squared. In your Bohr's atomic model, the energy is absorbed when an electron jumps from a lower orbit to a higher one, while the energy is emitted when an electron jumps from a higher to lower one. So your atomic excitation, that is when your energy is absorbed and your electrons jump from a lower orbit to a higher one, while you have an atomic de-excitation wherein energy is emitted when an electron jumps from a higher one to a lower one. The energy and frequency of the light emitted or absorbed can be calculated by using the difference between the two orbital energies. That is, you have your delta E is equal to 2.179 times 10 to the negative 18 of 1 over n squared minus 1 over n1 squared minus 1 over n2 squared. The energy for your atomic excitation and atomic excitation is equal to your hc over lambda. So what we have here is the structure of your atom, which we can say correctly describes how your atomic structure looks like. So you have your quantum mechanical model. In this model, your atomic orbital describes the probable location of the electrons. So it's not like you have your orbits where you can directly tell where the electron is. So what we actually have is an atomic orbital where in each atomic orbital there is a probability of finding an electron at that specific orbital. You call this one as your electron cloud. So it's not orbits, but it's electron clouds that can be seen in your atomic structure. The atomic radius was found to be around 10 to the negative 10 meters, and your nuclear radius is around 10 to the negative 15 meters. Some terms and constants. First, we have your atomic mass unit, where we use the symbol U or your AMU. This is used to describe the mass of your particles in your atom. And we are using your AMU or your U, your atomic mass. It's because the mass of your particles are actually very small. It's around 10 to the negative 20 plus grams. That's why it would be easier for us to use your atomic mass unit. Your AMU is 1/12 of the mass of carbon-12 atom, and that is equal to 1.66 times 10 to the negative 24 grams. As you can see here, your protons has a mass of 1.007278 AMU, or in kilograms, it is 1.672623 times 10 to the negative 27 kilograms. So just from here, you can see that it would be much easier if you use the atomic mass unit as compared to using the kilograms. Your electrons, on the other hand, has a mass of 0.000548580 AMU. It has mass in kilograms of 9.10939 times 10 to the negative 31 kilograms. Your neutrons, it has a mass of 1.0086665 AMU, or 1.674939 times 10 to the negative 27 kilograms. So as you can see, most of the mass in your atom is concentrated in the nucleus, where your protons and then your neutrons are. The mass of your electrons is very small compared to the mass of one proton. One proton is equal to around 2,000 electrons, and your protons and then your neutrons have near values of their masses. Now we cannot stop discussing your atomic structure in just your neutrons, your protons, and then your electrons, because as you well know, your protons and then your neutrons are not actually very fundamental, so they can still be subdivided into other particles. Like say for example, you have here your standard model of elementary particles. So we call your fundamental particles as your elementary particles. So you have your quarks, you have your leptons. For your quarks, you have your your charm, your top, your down, your strange, and then your bottom quarks. And then for your leptons, you have your electron, your muon, your tau, your electron neutrino, your muon neutrino, your tau neutrino. So as you can see, it's only the electron that is fundamental, while your proton, it's composed of 2 up quarks and then one down quark. And the other hand, your neutron, it's composed of 1 up quark and then 2 down quarks. The quark model was independently proposed by Murray Gell-Mann and George Schwig. It was first discovered in 1968 at the Standard Linear Accelerator Center. And as of now, we still have so many of these particles that are yet to be discovered. But these are some of the subdivisions of these quarks. And you also have here your force carriers, or what you call your bosons, your gauge bosons. So these are the fundamental force carriers. You have your gluon, your photon, your Z boson, and then your W boson. And then, of course, you have your scalar boson, which is your Higgs boson, the famous Higgs boson, the God particle. Also, we discussed about your 4 fundamental forces. So first in the list, you have your gravity, your strong nuclear force, your electromagnetism, and then your weak force. Your gravity, this is the force that is very known to us. You have an attractive force between masses, which according to the general relativity occurs as a result of the effect of energy acting on a space-time field. Another force that is known to us is your electromagnetism. This is the force that acts between electrically charged particles, like say for example your protons and then your electrons. This phenomenon includes the electrostatic force acting between charged particles that are at rest, and the combined effects of electric and magnetic forces acting between your charged particles moving relative to each other. And then we have your strong nuclear force. This is a force that we are going to talk about in our course. The strong nuclear force is what holds together the nuclei of your atoms. The protons and neutrons making up an atom's nucleus are themselves made up of a trio of simpler particles called the quarks. So as we have said earlier, you have your 2 up quarks and 1 down quark for your protons, and 2 down quarks and 1 up quark for your neutron. A particle called the gluon acts on a property of quarks called the color, creating the force pull. So you have your gluon that acts on your neutron and then your proton to hold them together. And we have the weak force, also another force that we're going to talk about a lot in this course, which describes how the quarks that make up nuclear particles can change from one form into another. The weak interaction of weak nuclear force is responsible for some nuclear phenomena such as your beta decay. So your strong force and then your weak force are the forces that we are going to talk about in these lessons. So again, you have here your 4 fundamental forces: your strong, your electromagnetic, your weak, and then your gravity. If we're going to arrange this one according to the strongest to the weakest of the forces, the strongest is actually your strong nuclear force, and the weakest of this force is your gravity. So you have your strong force, your electromagnetic, your weak, and then your gravity as the weakest of these forces. If we say that the strength of your strong force is 1, the strength of your gravitational force is just around 6 times 10 to the negative 39 of your strong force. It's easier for us to jump than to break your nucleus apart. Okay. These are the force carriers for your forces. For your strong force, you have your gluons, and then for your electromagnetic, you have your photons, and then the force carrier for your weak is your intermediate vector bosons. You have your W plus, your W minus, and then your Z bosons. And for your gravity, you have this force carrier graviton that is yet to be identified. So it's not yet found in nature, or it was not yet found in experiments, your graviton. Now, let's finally go to our actual lesson. So let's discuss the atomic nucleus. So these are the topics that we're going to talk about: the discovery of the neutron, the nuclear properties, the deuteron, the nuclear forces, nuclear stability, radioactive decay, alpha, beta, and gamma decay, and then your radioactive nuclides. So it was in 1911 when Rutherford proposed the atomic structure with the massive nucleus in the middle of your atomic structure. But it was just in 1932 that scientists knew what composed the nucleus. So during Rutherford's time, he did not actually know that there is a proton and a neutron in the massive nucleus. And in the 1990s or in the 1900s, the nucleus has been assumed to consist of protons and electrons. However, this was not widely accepted because of the following reasons. First is the nuclear size. So the uncertainty principle puts a lower limit on its kinetic energy that is much larger than any kinetic energy observed for an electron emitted from the nuclei. So according to the uncertainty principle, your electron should have this lower limit of kinetic energy when it is located in your nucleus. However, by experiments, the kinetic energy of your electron is much smaller compared to the kinetic energy stated in the uncertainty principle. So it's really not possible that the electron is inside your nucleus. And then another reason is the nuclear spin. If a deuterium consists of protons and electrons, the deuterium must contain 2 protons and 1 electron. And a nucleus composed of 3 fermions must result in half integral spin. But it has been measured to be 1 and not 1/2. Another reason is your nuclear magnetic moment. So the magnetic moment of an electron is over 1,000 times larger than that of the proton. So just from that alone, you can say that the electron is really not in your nucleus, but it should be something else. And the measured nuclear magnetic moments are of the same order of magnitude as the protons, so an electron is not part of the nucleus. So there is strong experimental and theoretical evidence that electrons are not bound in the nucleus. And in the 1920s, Rutherford proposed that a neutral particle called the neutron might actually exist. Okay. So again, in the 1920s, Rutherford proposed the existence of the neutron. But it was only in the 1930s that the German physicists Bose and Becker used a radioactive polonium source that emitted our alpha particles. So during this time, they did some experiments with your polonium-210 alpha source, a radioactive material, and when these alpha particles bombarded your beryllium foil, there is this unknown radiation that is emitted, and when this unknown radiation is again incident on a lead foil, there's an unknown radiation that can penetrate the lead. And when this unknown radiation is incident with your paraffin, 5.7 mega electron volt protons were produced. This electromagnetic radiation, which are photons, are called your gamma rays, which have energies of the order of mega electron volts. It's Curie and Huliot who performed several measurements to study these penetrating energy gamma rays. So they actually use different materials aside from your lead foil and your paraffin. Curie was the daughter of Marie and Pierre Curie. So the daughter of Marie and Pierre Curie also died due to radiation, similar to how her mother Marie Curie died. So in 1932, Chadwick proposed that the new radiation produced by the alpha plus particle on your beryllium foil consisted of your neutrons. So it was James Chadwick, who proposed this one. And his experimental data estimated the neutron's mass as somewhat between 1.005 U and 1.008 U. Not far from the modern value of your neutron, which is 1.0087 U. Other nuclear properties. The nuclear charge is plus E times the number Z of your protons. The simplest form of hydrogen has a single proton and a nucleus. So this is your hydrogen 1. And the next simplest is your deuterium and then your tritium. These are hydrogen's isotopes. Deuterium is also called your heavy hydrogen. It has a neutron as well as a proton in its nucleus. So again, in your hydrogen, it is only consists, or the nucleus of your hydrogen is only composed of your protons. The next simplest form of hydrogen, the deuterium, is composed now of your proton and then your neutron. It has a neutron as well as a proton as its nucleus. The next one, the tritium, it has 2 neutrons and 1 proton. So these are the isotopes of your hydrogen. The nuclei of the deuterium and tritium atoms are called here your deuterons, or your deuterons, and then your tritons for your tritium. Atoms with the same Z but different mass number A are called your isotopes. So these are, or this is how you're going to write the symbol of an atomic nucleus. So you have AZ, XN, where your Z is the atomic number, the number of protons. And then your N is the neutron number, the number of your neutrons. Your A, on the other hand, is the mass number, where your A is equal to your Z plus your N. And your X is the chemical element symbol. So sometimes we do not actually use this complete symbol. Like say for example, you have your oxygen 16. So for your for your oxygen 16, so we write it as using the symbol for your atomic nucleus. We write your oxygen with, you have your 16 and then 808. But you can also use your 1680, because you just know that your atomic your Z plus N is equal to your 8. So you can actually omit your 8. In some sense, like for well-known elements like your oxygen, we just have your 16O, or write it that way. Okay. Each nuclear species with a given Z and A is called a nuclide, and Z characterizes the chemical element. The dependence of the chemical properties on N, however, is negligible. That is why the N here is usually omitted. Okay, so you just usually see this one or this one here. Let's have the classifications of your nuclides. So again, when we say your isotopes, these are nuclides with the same Z, but different A, or nuclides of the same element. So you have again your atomic structure symbol, your AZXN. Okay, like say for example here you have your 131 I, and then you have your 125 I. So they have the same Z, which is 53, but they have different A. And then you have here the isotopes of your hydrogen, your 1H, and then your 2H, and then your 3H. We also have these classifications called your isobars. These are nuclei that have the same A, but different Z. Like say for example, your 99MO and then your 99TC. And then you have your isotones. These are nuclei with the same number of neutrons, so the same N. So you have 131I and then 132XE, 131 53I and then 132 54XE. If you're going to subtract your Z from A, you get the same N for both these elements. And then you have your isomers. These are identical nuclei but in different excitation states. Like say for example, here you have your technetium. Again, we have here your nuclear properties. Again, your atomic masses are denoted by the symbol U or your AMU. 1 U is equal to 1.66054 times 10 to the negative 27 kilograms, or this is equal to 931.41 mega electron volts per C squared, where your C here is the speed of light. And both neutrons and protons are collectively called the nucleons, are constructed of other particles called your quarks. Rutherford actually concluded that the range of the nuclear force must be less than 10 to the negative 14 meters. So it's a very short range force as compared to your electromagnetic and then your gravitational force. And you can assume that the nuclei are spheres of radius r. So your particles such as your electrons, your protons, your neutrons, and alphas, your alpha particles scatter when projected close to the nucleus. And it is not obvious whether the maximum interaction distance refers to the nuclear size, the matter radius, or whether the nuclear force extends beyond the nuclear force or your force radius. The nuclear force between neutrons is often called a strong force. That's why here we are referring to your strong force as your strong nuclear force. This is the force that governs the binding of your protons and then your neutrons in the nucleus. The nuclear radius may be approximated to be your R is equal to R naught A 1/3, where your R naught is equal to 1.2 times 10 to the negative 15 meters. And we usually use the femtometer with 1 FM equals 10 to the negative 15 meters, or the Fermi, because the nucleus is so small that it's not practical to use the meters in talking about the radius of your nucleus. And you can approximate the nuclear shape as a sphere of volume 4/3 pi R naught cube times 8. And it has the nuclear mass density of 2.3 times 10 to the 17 kilograms per m cube. And the neutrons are protons, and protons are fermions with spin quantum numbers s equals 1/2. So much for that. Let's talk about the deuterium. After the proton, the next simplest nucleus is the deuterium, or your nucleus of your H2. Okay, the deuterium mass is equal to 2.013553 U, while the mass of your deuterium atom is equal to 2.014102 U. The difference of this one, the mass of the deuterium atom and deuterium mass is equal to 0.00549 U, which is equal to the mass of the electron. And the deuterium nucleus is bound by the mass energy BD. And the mass of the deuterium can be determined from this one here. You have your MD is equal to MP plus, this is for your proton, your MP, the mass of your proton, plus your MN, the mass of your neutron, minus your BD, which is the mass energy, divided by c squared, the speed of light. So that's how you can determine the mass of the deuterium, or the deuteron. And let's discuss about the nuclear binding energies. So the binding energy of any nucleus, your AZX, is equal to the energy required to separate the nucleus into free neutrons and your protons. So if you want to disengage or to break down or to separate your neutrons from your protons, you need to know the binding energy of your nucleus. The binding energy is given by this formula. You have your binding energy B of your atom. That's equal to NMN plus ZM 1H, the mass of your the atomic mass of your hydrogen, and then minus M, and then this is multiplied to c squared. Okay, here your B is again your binding energy, your N is the number of neutrons, your Z is the number of protons, your atomic number, your M is the atomic mass nuclide, or the mass of your nuclide, and then your M 1H is the mass of your atomic hydrogen, which is equal to 1.007825 U, and then your Mn is the neutron mass of 1.008665 U. Just take note of these values here. This solving your binding energy is direct to the point. You just input the constants and then the values here, and then you get your binding energy. C squared here, by the way, is equal to 931.5 mega electron volts over U. Please look again at the formula for the binding energy. Does it look familiar to you? The nuclear binding energy formula. Okay. It actually is just your E is equal to mc squared. Your E here is your binding energy. Your M, your mass, is this mass here. And then you have your C squared. Okay, so it is just this formula here. Your E is equal to, the famous E is equal to mc squared. In simpler way, you can actually rewrite this equation. We can write it in a simpler manner. So we have your binding energy B. Let's just write it as your EB. You can use this one also. I usually use this one. Your binding energy EB is equal to your N, the mass of your neutron, plus your Z, mass of your atomic hydrogen, minus the mass of your nuclide. So you have your AZM, and then times C squared. So your binding energy EB is equal to your N, your number of neutrons, times the mass of the neutron, plus your number of protons, or your atomic number, times the mass of your hydrogen, minus the mass of your atomic mass nuclide, your AZM. So it's much easier for me to remember if I use this one than use this one. But they're just similar terms. You just have to remember these constants here, okay, in solving for your nuclear binding energies. Now let's talk about your nuclear stability. Your nucleus should be stable, because if not, it may undergo some metastable states, or it may decay, or it may transform from one form into another. And when can you say that your neutron or your nucleus is stable? So again, you have here your binding energy formula, which presents a method to determine the binding energies in terms of the atomic masses. Your nucleus is stable if B is positive. Okay, if B is positive, the nuclide is said to be stable against dissociating into free neutrons and electrons. And it can only be positive, however, if this one here is smaller compared to the combination, to any possible combination of these two here. Because a nucleus containing a nucleus is said to be stable if its mass is smaller than any other possible combinations of a nucleus. So that's the only way for this one to be positive. But there are actually dissociations wherein your binding energy is negative, but your nucleus is stable. So if that is the case, there may be other reasons why your nuclide is stable. So from this, we need to have a general form of your formula here to take into consideration those dissociations of your nuclides which are stable, but you have a negative binding energy. The binding energy of a nucleus against dissociation into any other possible combinations of nucleus, example nuclear R and S, is given by this general form now. So you have your B, Mr plus Ms minus M AZX times C squared. And this formula here can be used to find the separation energy, your proton or your neutron separation energy from your nuclide, which is the energy required to remove one proton or one neutron from a nuclide. And what you see here is the Segre chart. So it's spelled as SEGRE. So your Segre chart. So this is a chart where all stable and unstable nuclei that are long-lived enough to be observed are placed. This is actually an interesting chart, and you will see later in the next slides why. So this is another chart, another form of the chart. Your Segre chart or your nuclide chart plus the proton versus your neutron number. So for this case here, you have your, sorry, for this case here, for this chart here, in this axis is your protons. And in this axis, you have your number of your neutrons. The earlier chart, it was given in vice versa. So the y-axis is in neutrons and then the x-axis is in protons. So it can be just interchanged. And your second chart it displays the schemes, the decay schemes, or the nuclear transformations, such as your beta decay, your alpha decay. Okay. And again, and also it from here you can easily see your isotopes, your isotones, your isomers, and then your isobars. You just remember that your isotopes, you have same Z, T here, the number of protons, and then your isotones, same N, so you have your N, and then your isomers, your Z and A, and then your isobars, your with same A. So this is a technique in order to remember what your isos are. Okay, now you can have a view of this Segre chart from this website, and I will be giving it to you. Okay, and in this website you can play with this chart. So now the next question is this just like an island? So what is this really? What does this chart really looks like? So let's zoom out. Let's zoom in. And this is what you're going to see in your nuclei chart or your Segre chart. So these are actually composed of many of your nucleides, stable and then your unstable nucleides. Let's zoom in more. So this one here. So you can see now your stable nucleides and the block ones, and then you have this one here. You can see now your other nucleides and their decay modes, and then yeah, that's it. So it's actually a very large chart for your nucleides. So please explore this one in the website. Let's go back to this form here of your nucleide chart. Okay, the block lines here, or the block or the elements which are in color block are actually your stable nucleides, and they can form a line which we call your line of stability. This line represents the stable nucleus, and it actually appears that if your A is less than or equal to 40, that is the sum of your N and Z is equal to 40. The nature prefers the number of protons and neutrons in the nucleus to be about the same number for your nuclide to be stable. Let's see from here, your 10 neutron number, and then your 10 proton number. So here it's stable for your 20 neutron, and then your 20 proton is still stable. Okay, so it's 20 plus 20 is equal to 40. So if it is A is less than 40 or equal to 40, you have an equal number of neutrons and protons. You have you can see stable nucleides. However, if you go higher, let's say if we still look at the same number of protons and the same number of neutrons for 30 neutrons and 30 protons, you cannot anymore observe these stable nucleides. So it's somewhere upward from this N equals Z line. So for A is greater than 40, there is a decided preference for N is greater than Z. So it is preferred that your N is greater than Z for your A greater than equal to 40. So it's preferred that your N is greater than Z so that your nuclide be stable. And this is because the nuclear force is independent of whether the particles are neutron-neutron, Newton-proton, or proton-proton. So this is how you're going to explain why it's preferred when you have more neutrons, okay, as compared to more protons, because as the number of protons increase, The Coulombic force between all the protons becomes stronger until it eventually affects the binding energy. So we've actually talked about your strong force is the energy that binds your protons and then your neutrons together. If there are more protons, then it may be that the force that will now govern is your electromagnetic force, which is the Coulombic force between uh, your protons. So as you can see here, the red spheres are your protons, and then the blue spheres are your neutrons. If there are more protons, there will be more repulsions between distant protons, as compared when you have a lesser number of protons. Here, you have the attractive force between the adjacent nucleus that can balance your atomic nucleus. So we do not want that, or a stable nucleus do not want that it has more protons because of the repulsive force between the protons. And if you have more protons, then your atomic nuclei may not be stable. Okay. Again, your nuclear stability is just the stability of your nuclei, which is a function of your neutron to proton ratio. For A is less than 40, you have a stable nuclei which have a ratio of n over z equal to around 1. That is, your n is equal to z. And for A greater than 40, you have a stable nuclei with a ratio n over z of around 1.7. For heavy nuclei, the nucleus will have a preference of fewer protons than neutrons because of the large Coulomb repulsion energy. And most stable nuclei have both even z and even n, or your even nuclei. And you can only observe 4 stable nuclei which have odd z and odd n, or your odd nuclei. These are the magic 4: your H2, your Li6, your B6, and then your N14. And this table here tallies the number of stable nuclei. If you have even n and then even z, your even nuclei, you have 166 stable nuclei. And then if you have an even n and odd z, you have 53 stable nuclei. For odd n and then even z, you have 57, and then for odd there is only 4 stable nuclei. Okay, so this list here, so this stable nuclei here, you can see it in the block lines, or you can see this one in the block tiles of your Segre chart. So now let's talk about your radioactivity or your radioactive decay. So your radioactive decay or your radioactivity is the decrease in the amount of any radioactive material with the passage of time due to the spontaneous emission of particles and electromagnetic wave. And this also refers to the spontaneous disintegration of your atomic nuclei. So as you can see here, in the beginning you have 239 polonium, but this one is not stable, so it may decay into 235 uranium in this case. So it was Marie Curie, her husband Pierre Curie, along with other scientists Wilhelm Röntgen and Henry Becquerel, who discovered radioactivity. And Marie Curie and her husband discovered some of these radioactive materials, polonium and radium, in 1898. The simplest decay form is that of the gamma ray, which represents the nucleus changing from an excited state to a lower energy state. Other modes of decay include the emissions of your alpha particle or your alpha decay, and then your beta particles or your beta decay, your protons, your neutrons, and then your fission. And this radioactive decay can be mathematically explored using the disintegration or the decays per unit time, which we will refer to here as the activity. The activity R is equal to your time derivative of your n. So you have your negative dn over dt, where n is the number of your unstable atoms. dn over dt is negative because the total number n decreases with time. And we want to have a positive activity. The SI unit of your activity is in becquerel. So 1 becquerel is equal to 1 decay per second. And other units recently used is the Curie or your CI. 1 Curie is equal to 3.7 times 10 to the 10 decays per second. Now, if n of t is the number of radioactive nuclei in the sample at time t, and lambda, which we'll refer to here as the decay constant, is the probability per unit time that any given nucleus will decay. So we have your activity R is equal to lambda times n of t. And your dn of t, which is equal to your negative r of the r dt. This is just your activity formula. You can equate this one now to your to the negative of lambda n of t dt. So it's just from here, from the first part of your equation, and just rearranging your equation, this one here, this leftmost side and then the rightmost side of your equation. So we have dn over n, and then the other you have negative lambda dt. We integrate that one, you have the integral of your dn over dt, which is equal to ln n. And the integral of your negative lambda dt is just your negative lambda t plus your constant. And we remove this ln, your natural logarithmic, by multiplying it with your e. So multiplying e on both sides, you have n of t is equal to e of negative lambda t plus some constant. And if you let your n at time equals 0 to be n naught, then your radioactive decay is equal to your n of t equal to n naught e negative lambda t, where lambda is again your decay constant, and then your time is your time in seconds, and your n naught is the initial number of your radioactive nuclei, and then your n of t is the number of your radioactive nuclei after some time t. This is your radioactive decay law. The activity R is going back to the equation, to our first equation. The activity R then is now your lambda n of t, which is equal to your lambda m naught e negative lambda t. So we have R naught e negative lambda t, where here your R naught is the initial activity at time equals 0. And it is common to refer to the half-life T1/2 or the mean lifetime tau rather than the decay constant. The half-life is when your radioactive nuclei, the number of your radioactive nuclei is half that of the original number. So you have your n at T1/2 is equal to n naught over 2, half of your original n naught. So you have n naught e negative lambda T1/2. And we take the ln of both sides. Okay, so ln 1/2 is equal to ln e negative lambda T1/2. We do this one so that we can solve for your half-life T1/2. Okay, so ln times e, so it's just negative lambda T1/2. So we can now take out your T1/2 of the equation, and the half-life now is just your negative ln of 1/2 over lambda, or this is just equal to ln 2 over lambda, or you have your half-life T1/2 is equal to 0.693 over lambda. So to find for the half-life of your nucleides, you just need to know your decay constant. So you have your 0.693 divided by your decay constant. And the mean lifetime tau is 1 over lambda. You have your T1/2 over ln 2. So this time let's have an example on calculating your activities on your radioactive decay. Calculate the activity of a 30 megabecquerel source of your 24 sodium after 2.5 days, given its half-life of T1 half is equal to 15 hours. What is the decay constant of this radionuclide? So again, calculate the activity of a 30 megabecquerel source of 24 sodium after 2.5 days, given its half-life of T1 half is equal to 15 hours. What is the decay constant of this radionuclide? Now for this problem, we are asked actually of two targets. So here our targets are the following. One, we are asked of the activity R, and then the second one is the decay constant lambda. Okay, so let's solve this one. Remember that your activity R is equal to your R naught times your E, negative lambda T. But before we can solve your activity R, we need first to find for your decay constant lambda. And your decay constant lambda is related to your half-life, which is your lambda is just equal to your 0.693, which is just your ln2 divided by your T1 half. And you can use this one, we can use your R's. So your lambda is equal to 0.693 divided by 15 hours. And your lambda, this is equal to 0.0462 per hour. So we now have our lambda, and we can now solve for your activity R. But take note here that we're asked of the activity after 2.5 days, and this is different with your half-life, which is given in hours. So it's better if you convert one of the constants, the unit of one of the constant into another. So for this case here, let's convert your 2.5 days into hours, so that here, this part here, we can cancel your hours, your hour term. Okay, so your 2.5 days, there's some conversion. You know that one day is composed of 24 hours. So you have one day, and your day unit will cancel out, and you will have here 60 hours. Now we can use this one, your 60 hours, to calculate for the activity. So we have R, that is equal to your 30 megabecquerel. Okay, your 30 megabecquerel times your E, negative lambda, which is 0.0462 per hour, times your T, which is 60 hours. So you can cancel your R's, your R unit. Okay, your R unit can be canceled out, and you get now your activity after 2.5 days of equal to 1.88 megabecquerel. Okay. So let's end our lesson here, and on the next lesson, we're going to discuss about your different decay modes.